Good morning, my name is Paolo Piccinini. My tutor is Professor Andrea Prati, and my co-tutor is Professor Rita Cucchiara. This morning I talk about 3D multiple object segmentation for a beam picking application. My research activity is split in two parts. I spent the first part of this year studying the smoke detector for a video surveillance system, and in the second part I work at the topic of this presentation. Due to time limitation, I can't give you an in-depth description of the smoke detector system. I want only say that this system led to 3 publications in international conference. Now, let me introduce the beam picking problem. The term beam picking refers to the problem of having a robot automatically picking an object from a beam containing multiple instances of the same object. More applications have been developed in recent years, but they work well in some simplified situation. The general beam picking problem, where the objects have a 3D shape and are randomly organized in the scene, are not complete solved due to the occlusion problem. Moreover, this previous approach were object dependent, and each object was modeled by a CAD model or in other complex way. Our goal instead is to develop a new system, object independent, without previous knowledge about the object model. It's important to say also that all the previous models were designed for mechanical parts like this. Instead, our system must handle pharmaceutical or cosmetic objects. This is the scheme of our test bed. Here there is the stereo pair. This is the laser projector, and this is the beam containing the object to take out. In the rightmost part of the slide, you can see 2 pictures of the real test bed. The beam picking problem was split in 2 parts. The first one is the 3D reconstruction in order to discover the distance between the cameras and the object. And the second is the 2D segmentation in order to discover the object position and orientation in the beam. I don't spend much time talking the 3D reconstruction. I use a well-known method based on the laser stripe, and these are 2 examples of the reconstruction. The 2D segmentation is divided in feature extraction and matching and object segmentation. The feature extraction and matching is based on the SIFT, that is a well-known algorithm developed by SIFT in 2004, and the object segmentation is composed by object localization and pose estimation. The object localization is performed by a voting scheme. In the model, for each key point extracted by the SIFT, a vector distance between the key point itself and the center of object is computed. And now, in the current image, for each key point matched with the model, the vector distance is reported. Since the vector projection is not accurate, a cloud of points is formed. Then, the object center position is given using a clustering algorithm called mean shift. At last, there is a validation step. For each cluster found with the mean shift, center is considered correct only if it has a minimum number of votes. Finally, there's the pose estimation that is directly derived from the object segmentation. I don't know if you can clearly see the pictures. In the model, the white circle are the key point extracted by the SIFT. The full green circle is the object center, and the red crosses are some principal point fixed by the user. For the key point, I compute the distance between the key point itself and the principal point, and then I look for some matches in the current image. In the current image, only the key point related to a valid center, only for this key point, I report the vector distance computed before. Knowing now, I know the location of the principal point in the current image. Knowing this point in the current image means knowing the object orientation. And now I'm able to say where the object is and how is it oriented. Finally, there's some segmentation in working condition. Here there are 3 objects. Probably you can't see it. Here 5, and finally 6. And this is the list of my publication. So that's all. Thanks for your attention.